Alrighty, my friends, what is going on? As always, no matter where you are, I hope things are going fantastically well for you. Now, my name is Dr. Jason Dinsmore, aka the OChem Whisperer, and I want to help you succeed in your organic chemistry class. Now, what are we going to be going over in this lecture? So what I want to do is I want to show you how to understand synthesis of alkynes. Okay, we've got basically, it's really kind of two syntheses that we're going to work through. They're going to be very similar, as you're going to see, but I want to do this one specifically to show you some key features of things to think about when you're working with alkynes. All right, so let's go ahead and do this. All right, so this is what I want to focus on first. What I want us to do is I want us to look at forming a cis diol, two OHs, and two trans OHs, okay? So that's what I want you to think about here. Excuse me. So the first one, the top one is going to be our trans OH groups, and the bottom one is going to be our cis OH groups, all right? So as I'm going through here, if you want, go ahead and pause this, kind of map out a synthesis of how you think we might be able to do this before we go ahead and dive in, all right? Because like I always say, it's important that you work through this before I actually go through it, because I want you to be a rock star here so you can take that with you on your exam. All right, cool. So let's go ahead and take a look here. So what I'm going to do is I'm going to put the trans OH or the trans diol at the top kind of as a reference point. And I'm going to show you, we're going to refer to that, and I'm going to show you what's most important when we look at that, all right? So let's go ahead and start with this alkyne right here. We're going to notice this is an internal alkyne, so we have carbons on both sides, okay? And I'm going to point this out that I'm just going to assume that all of you are pretty comfortable with your function groups now, and then I'm going to kind of work through this kind of fast because I want to show you things, key features to think about. So this would be kind of more on the intermediate to advanced level in terms of synthesis, in terms of working through this. But really it's for anybody. Even if you're just starting out, these are going to be key principles that you want to think about, all right? So if we start with this alkyne right here and we look at our final product, we want a diol. In order to get a diol, we need our intermediate to be a double bond or an alkene. So we need to remember this chemistry in terms of taking an alkyne to an alkene. And there's two basic ways of doing that. The first one that we want to do is we can use H2 and Lindlar's catalyst. Remember, Lindlar's catalyst allows us to get a cis double bond, okay? We don't want to use H2 and palladium on carbon or just a metal because that'll take us all the way to the alkane, the single bonds. We want to stop at the alkene, all right? So that's going to give us a cis, but we also want to remember that we can get a trans double bond. So if we use sodium and ammonia, sometimes you may see lithium, but the basic one that you're going to see is sodium ammonia. That will wind up giving you the trans double bond, okay? So we're going to find out here that it does make a difference whether you use a cis or a trans double bond when you're doing stereochemistry, and that's why I want to show you this one specifically, okay? So now what we want to do is, in this case, we're going to start with a dihydroxylation, and we're going to use osmium tetroxide, or OSO4. You may have also seen KMNO4, but I'm going to use this one right here. And you want to remember that OSO4 always gives you a cis dihydroxylation, and I'm going to show you how that's going to come into play here, okay? So if I take this and I add it to our alkene, we can see that we're going to get a dihydroxylation. In both cases, they're cis. Now I want to take some time to explain that. Now you're going to notice that both of the OHs on the top one are pointed up, and the bottom structure there's an OH up and an OH down. The fact that you have OHs on the same side, or let's say OHs on the opposite side, that does not mean cis or trans, okay? The key that I want you to pay attention to is it's the dashes and wedges when you have single bonds that's going to allow you to tell whether it's cis or trans. When you have groups up or down, that's usually going to be based off of a double bond, which we saw as our structure prior to that. So in this case, both of these are cis because they are both wedges, or I could have drawn them both as dashes. It doesn't matter. I'm just decided to pick one. You can pick one yourself. But in both cases, those are cis, okay? Now, I'm going to highlight this here. So the top one is cis OH groups, and the bottom one is also cis OH groups, even though they're kind of on different sides, okay? Now, the key that I want to show you here is, let's go ahead and look at the actual carbon framework, not the dashes and wedges, but what the carbon structure looks like. You'll notice on the bottom one, it's similar to the one that we have in the box on the top. And that's a typical way that we see linear structures, right? As we go that up, down, up, down, up, down. It's like a sideways staircase or a kink structure. But that's the basic structure that we're looking for. And we're going to notice that if we look at the top, that's how I'm basing all of my cis and trans off of. So one thing that you want to think about is when you start forming cis double bonds, you want to make sure that we'll see here in a minute, that you want to rotate that carbon framework because you want to get it in the same framework that you have in your structure, okay? So we're going to see that the only one that matches up with our cis and our trans double bonds that we initially saw at the beginning is the bottom one. So we can see how we have our carbon framework that's kind of that up, down like that. It matches. So in this case, we've made our cis OH, but you can see between the two groups, we do not have our trans OH, all right? So just take some time, pause it, make sure that you see what I'm saying there is that we want our carbon framework to kind of be in that up, down with our peaks and our valleys, not going around, which the top one, which kind of right here, the top one looks like a cup, okay? But what I want to show you is check this out. I want to show you if you ever get into this situation. So if you ever wind up doing a cis double bond, and you can see the top one like we talked about, it's kind of like a cup shape, what you need to do is you need to rotate around your bonds to make sure your carbon framework matches up with the structure that your professor provides or the one that I provide. So what we're going to do is we're going to rotate around that red bond. We're going to rotate around that so we can wind up getting our OH and our carbon structure basically in the kinked framework. And when I do that, it looks like this. So the first thing that I want you to notice is check out our carbon framework now is in the plane of the paper and it's at up, down, up. We've got it matching the structure up top. The other point that we need to pay attention to is when we rotate bonds like that, we rotate them basically from, we got our methyl that's down all the way flat in the page. Now it's flat, kind of pointed diagonally up. We rotate our dashes and wedges. So when you rotate bonds, you rotate dashes and wedges. If you were to look at the R and the S on that stereochemistry has not changed. It would still either be an R or it'd still either be an S. I haven't done that. You can double check for yourself. All you're changing is whether it's a dash or wedge. You're just changing the way that it's in 3 dimensionals, whether relative to us. So we rotate that. Now we can see that we've got our carbon framework in the correct way. And now we can see that one right there winds up giving us the trans. So we can see that in this case, when we use the Lindlar's catalyst, we get the trans OH. And when we use the sodium ammonia, we wind up getting the cis diol or the cis OH groups, okay? So just go ahead and pause it. If you haven't caught all that, make sure that that all makes sense, all right? Like I said, I know I'm going through this a little faster, but I'm assuming the fact that at this point in time, you're just kind of looking for kind of tips in terms of thinking about synthesis, all right? Now, what I want to do is I want to show you the same synthesis, but I want to do an epoxidation rather than a dihydroxylation. Because remember, dihydroxylations, as we saw, always give us a cis when they add, okay? So let's do the same thing with an epoxidation. I'm going to flip. Remember the last time I did the cis alkene on the top and the trans on the bottom? I'm just going to flip it just to change it up. So in this case, we can see we're going to get a trans double bond or we can get a cis double bond. And now we want to see with an epoxidation, what's the difference? What happens, okay? So in order to do an epoxidation, there's going to be a 2-step process ultimately leading us to our dihydroxylation or our 2 diols, 2 hydroxide groups. We're first going to do an epoxidation. We can use hydrogen peroxide. You can use MCPBA. You can use some sort of other peracid like a peracetic acid. I just wanted to use hydrogen peroxide, okay? Then the second step, in order to give us our diol, we need to add an acid and water, okay? And if you're not sure exactly how that's going to work, you can always go back and rewatch, not now, once we're done with this. After we're done with this, go ahead and rewatch the epoxidation with acid catalyzed addition, and you can see how we form that, okay, if you're not sure. So if we do this 2-step process, we want to remember the first one we're going to want to do is the epoxide is always going to be cis or syn, okay? Because that 3-membered ring, there's no way to get a dash and a wedge across that triple bond, or sorry, the triple bond, across that, that 3-membered ring, okay? But what I do want you to notice is the relative orientation of our methyl groups, in this case, or our carbon group, stays the same. So here it's quote-unquote trans, and the bottom one it's quote-unquote cis, okay? That's going to be our initial epoxidation. Then when our water comes in and attacks, we always get a trans diol with epoxidations, okay? With the OSO4, we always got a cis diol. With the epoxidation followed by nucleophilic attack, we always get the trans diol. But we're going to see once again that we have the same issue that we had before. We're going to see that here, our top one in this case, we have with the same thing, we have our trans double bond. We can see that our carbon framework is up, down, up, which matches the top one that we start out with in the box. So we can see our carbon framework is already matched up. We don't have to rotate anything. So in this case, we did indeed get the trans diol, but we're missing the cis diol. So just like before, what you're going to need to do is take this bottom structure, rotate it around that red bond, and ultimately redraw the structure. Now, I'm not going to do that for you on this one. I want you to redraw that on your own and confirm the fact that when you rotate that, you do indeed get the cis diol. The other thing that I want you to do is I want you to see the difference between when we made our cis and our trans double bonds in this one with the epoxidation versus when we made the cis and trans double bonds when we did a dihydroxylation. Notice the difference in terms of where we got our cis diol and where we got our trans diol. You're going to notice there's a slight difference, all right? All right, and that's all I have for you today. And as always, thank you all for coming on here. I absolutely love to get to chat with all you, see what you all are up to. And until next time, I hope you all have a good one.